Okay, so well, let's begin. So today we're going to have two sessions. So I'm delivering the first session on basic of modeling, and then following that we will start looking at forecasting models. So Mitch will cover regression in the next session, and then tomorrow we will cover exponential smoothing and ARIMA families. On Friday, we focus on evaluating the quality of the forecast. So let me share my slides. Okay. Do you see my slides?
Yes, they're coming through, Bahman.
All right, thank you. Okay, so what we're going to cover in this session, well, first of all, we go through a definition of a forecasting. I know that in day one, we had a definition of what a forecast is. So today we revised that definition. And in my opinion, this is a better definition of the forecast. And then we look at forecastability, because of course, if you talk about forecasting, the question is, what can we forecast? Is everything that we want to forecast is forecastable? What are some criteria that make something easy or difficult to forecast? And then for the rest of the session, we are actually focusing more on the Fable ecosystem and how we do the modeling and forecasting in Fable. And I think this is actually one of the most important sessions, because whatever we do later somehow is relying on this. And if we learn how we do this, how we specify models, how we estimate parameters, how we produce a forecast, how we extract information, and how we visualize the forecast. So the rest of the session is the matter of understanding the models really, and then how we use them within these frameworks. All right, so again, you remember the forecasting workflow. So far we have looked at different steps up to step 5. So of course, we haven't covered some of them in detail because they are out of scope for this training. That's why the main focus has been on step 4 and step 5. And today we are going to look at step 6 and step 7. And of course, tomorrow we will talk more about models and how to produce forecasts using them. And of course, the next session as well. And Friday, we look at the step 8 here. And then if you focus, regardless of this basically workflow, if you just focus on the statistical forecasting steps, because forecasting also could be judgmental, not using statistical methods for instance. So here, of course, we prepare data, visualize them, choose and fit models, produce forecasts, and evaluate the quality. And now, basically, by going through the rest of this, we are going through the entire forecasting steps and what you need to produce a forecast and evaluate it and use it for informing decisions in real world. So now, what is a forecast? So this is, if your domain is a statistic, probably you understand this probability distribution easily, but if you are not, then we go through this, so don't worry, we will understand what we mean by a probability distribution or different possible outcomes. So if you have used forecast before, most likely when you talk about forecast or you hear about the forecast, people mean a single number. So let's say we forecast the demand or a sales of an item for tomorrow, and then that forecast is 400, right? And that 400 is one single number. This is typically what people understand as a forecast, and we call it a point forecast. But a forecast should acknowledge uncertainty in the future. So we know that the future is uncertain. But if we use a single number or as a point forecast to represent our understanding of the future, it doesn't really acknowledge uncertainty. So in order for a forecast to acknowledge that, we need to have this definition of a forecast as an estimate of the probability distribution of a variable to be observed in the future. So basically, by saying that, we acknowledge that we may have different possible outcome for whatever variable we want to forecast. And then, of course, these possible outcomes may have different likelihood. So now let me show you how we do it. So this is a time series of short-term tourism visitors to Australia. We had looked at something similar to this in the past sessions. So we had looked at the quarterly time series. This one is a monthly time series. So we have months in x-axis and we have thousands of visitors in y-axis. So if we fit a model, again, we talk about how we do it later, and then we simulate from this, we can get one possible future. So remember, these are this line, they are points. So we have about 48 periods that we forecast. We link them together and we get this line, and this is one possible future. We could actually do the same, so repeat this process and create another possible future. And then by repeating this process, I can get 10 or even 1,000 possible future. And if you get this 1,000 possible future, sometimes you may need more, like 5,000. Some people even go to 1,000,000 possible futures. And then if you do this, you will get a region where the actual will lie, but of course we don't know exactly where. Now, if you put all this thing together, now we get all this, the region where the actual in the future may lie. And then if we take an average of all these possible futures in each period, we get this blue line. This is our point forecast. So if we, let's say, have a definition of a forecast as many possible futures, and we can also represent them as a distribution if you want, and then in each period, we take an average across all those possible futures, we also get the mean, right? Which is the point forecast that we are referring to. Of course, we can also extract the intervals from this. So here we have two different intervals, in light blue and dark blue, 50% and 95% prediction intervals. So sometimes we need to make sure we don't confuse prediction interval with what we call the confidence interval. So prediction interval is about forecasting, right? Confidence interval is not, it's about estimating in general. So in more technical term, in prediction interval, we have both reducible and irreducible errors. And by irreducible error here actually we're referring to randomness, something we cannot predict or forecast at all. So basically, the idea here is instead of defining a forecast as one single number or a point forecast, we define it as estimate of probability distribution, and we can create this trajectories that we saw, different paths. And then from there, we can get prediction intervals, and we can also get the point forecast, mean or median, if you want. We can represent them also as a distribution, like as a histogram, for instance. So in this example, we have a daily time series, and we forecast for 7 days, and we produce the probabilistic forecast, and we create the histograms, and then the points there also in these points in white also are a point forecast, and we can link them together. We can also actually represent them as a density plot. And of course, this is like a normal distribution. Of course, we could have different type of distribution here, but in Fable, we are mainly covering normal distribution as a forecast distribution. So again, if you are familiar with distributions, the interpretation of a forecast distribution is similar to any distribution. So in x-axis, you have different possible outcomes for whatever variable you're forecasting, and in y-axis, you have likelihood of them. So you have the center of the distribution. You can have a point forecast as a mean. You can have a median as well, and you can have any quantile from that distribution. And the prediction interval that we also highlighted is, of course, is corresponding to a quantile from that distribution. So the idea here is, if we get the entire distribution for the variable that you want to forecast for any period that you want in the future. From that distribution, you can extract any information or any moment, if you like, from that distribution, including the mean, median, mode, and any quantile. And this is really what we need to inform decisions about the future. Okay, so this is basically the definition we provide for the forecast, right? So now, whenever you hear about the forecast, you need to make sure by a forecast we don't simply mean a single number or point forecast, but the entire distribution. So these are some notations that you may see in the slides later or later in the book that you need maybe to remember. So here we have the forecast to be forecast, the variable to be forecast or thing to be forecast. So we represent it as y, t plus h. So h here is our forecast horizon, right? So how many periods in advance you want to forecast. So if you want just to forecast one period, like tomorrow or next month or next week's h is 1. So if h is 2, so it means if you have a daily time series, you forecast tomorrow and day after tomorrow, right? So h represents the forecast horizon. So this is the information that we have. So we have the time series from the beginning, from the period 1 to the last period. So t here represents the last period. And then we are interested in the forecast distribution that we represent as yt plus h, given, right? We have the data or the time series from period 1 to the last period or period t. We can extract the point forecast from it as expected value of that distribution. We can also extract the variance of the forecast from it. And then we can get also the prediction interval for any range that you want from that distribution. So most of this is implemented in Fable, and it's quite easy to get this information out from the distribution variable, and we will learn how to do it later. So there was one. Yeah, so now the question is, again, going back to the first example where we had this time series, right? Again, this is the time series of monthly visitors to Australia. You can see actually this, that it has quite a strong signal. You see that repetitive pattern within a fixed period of time, which is a definition of seasonality. So it's a strong seasonality. And then a bit of a trend as well. And actually what happens is, if you look at the model that we use for this time series, so from, let's say, January 2018 to about February 2020, you see that, so the black line is the actual, and the blue line here is the point forecast. And then you have, of course, two prediction intervals, 50% and 95%. You see that in many cases, the point forecast is quite close to the actual, but in the dark or the black line is within the interval as well in many cases. So the model does a decent job up to now. And then something happened here. Anyone can guess what happened here? So what happened here is the actual is very different from the forecast. So something happened. Can you put in the chat if you know what happened here? Yeah, so absolutely, yeah. So COVID happened here, and of course, lockdown and restrictions in travels, and we cannot travel. And so it's almost zero, right? The travels, the number of visitors. But then the model is doing something similar. And this is, again, the definition that we had in the first session about forecasting, right? In the forecasting, we try to capture systematic information that we have in the time series, and we use it to forecast the future. So in a way, we assume that those systematic information we observe in the past, we observe them in the future as well. But in a case like COVID-19, of course, that didn't happen. So model is doing similar thing, assuming that we have those strong components we observed in the past, but the reality was different. So this brings an important question of what can we forecast? Of course, there are many things that we can forecast. When it comes to financial market, there are many different variables you might be interested in, like closing price of Google or Facebook, for instance, stock market. You might be interested in also forecasting the currency exchange rate. You might be interested in forecasting the sales of pharmaceutical products. We can also forecast the demand, the electricity demand or load. And of course, one thing that we also see almost every day is the weather forecast. And of course, if you are in the area of forecasting and you talk to like general public, when you talk about forecasting, this is the first thing they ask you. And actually, my wife blames me all the time when she looks at the weather forecast and we go out and it says not raining, and then there is a bit of rain. They say, oh, your forecast is always wrong. So, but this is a slightly different type of forecast, but this is a forecast as well. And you may think or not think about the time of sunrise or sunset as a forecast, but this is also a sort of forecast, but also any astronomical events like comet, for instance, we can also forecast them. So here there is a list of different things that we can forecast, but you could also add anything you want to this list that is more aligned with your own area of research or area of interest in general. So daily electricity demand in 3 days, timing of the next Halley's Comet appearance, time of sunrise, this day next year, Google stock price tomorrow, Google stock price in 6 months, and maximum temperature tomorrow, but this could be, for instance, in the airport of your city, exchange rate of US versus Australian dollar next week, and total sales of drug in Australian pharmaceutical next month. So this is a list. Now, could you reflect on this for a couple of seconds and just tell me what is possibly the easiest thing to forecast from this list and what is the most difficult one? And then I can understand that this could be also a bit subjective. So there is no definitive correct answer to this. But if you could put your thoughts on the chat, that would be great. So I can see, yeah, there are answers. So it seems like a couple of answers say 3 or 1. Easy. So put easy first, and then when we are done with that, we can put the most difficult one, if you like. So we say easiest is 1. We have an answer, say easiest is Google stock price. Easiest is Google stock price, yeah. Which is actually this one. Easy 3, difficult 2. One, 3, difficult 7. So yeah, I think we see some answers. They are also somehow aligned with what I think. For instance, I think a lot of answers we saw around 3, time of sunrise. That is easiest, and I think I saw also answers around 7 to be difficult. So if I again, if I rank them in a way, so time of sunrise, time of the comet appearance, temperature tomorrow, and then daily electricity demand, and then total sales of drug in Australia, and then stock price tomorrow, exchange rate, and Google stock price in 6 months' time. Possibly this is how I would rank them. Again, this is, as I said, is subjective. You may have slightly different view on this, but I think we could agree on, for instance, there are certain forecasts here that definitely are easier than others, regardless how we place them in the ranking. For instance, exchange rate or Google stock price in 6 months are very difficult to forecast. But the time of sunrise and the time of, let's say, comet, this is not the type of forecast we typically do, of course, with the sort of statistical forecasting we do. There are many more things involved there, but these are actually very accurate in general. And you can check it for yourself, the time of sunrise or sunset, for instance. Now, the thing is, first of all, how we measure something is easy or difficult to forecast. That's one question. And then, of course, the most important question that we will discuss is what makes something easy or difficult to forecast. So, and I think this is important to understand, because regardless of what forecasting problem you have in hand, you have to reflect on some of this before embarking into data analysis and building models to produce a forecast. Mitch has, I think, already mentioned entropy when he covered the time series features. When we extract features, one of the features that help us to actually think about how easy or difficult a time series is to forecast is entropy, which is highlighting the ratio of signal to noise. Now, when it comes to what makes something easy or difficult to forecast, what comes to your mind? Let's focus on, let's say, the easiest one. If something is easy to forecast, what are the reasons for that? And then you can maybe focus on daily electricity demand in 3 days' time. This is not too difficult to forecast accurately. So what could be the reason? What makes something easy or difficult to forecast? What are the criteria for this? So if you have any thought on this, please put it in the chat. Yeah, so I can see that availability of the data. And then I can see time frame, duration, or proximity. So I'm not sure what you mean by that, but that could mean, how far into the future we want to forecast. So I think, yeah, there are a lot of answers about data availability, enough data. Yeah, so how many factors affect the data? Yeah, of course. Yeah, and of course, reliability of data is important as well. Well, if you have a lot of data, but they are not like a good data, they're not accurate, the quality is not good, then it wouldn't be that helpful. Yeah, so there are a lot of answers about the data, which is, I think, important. So without data, it would be hard to produce forecast. And then, yeah, there is an answer saying all external influencing factors are known. This is also correct, but we never be able actually to understand all factors, but we try to understand factors contributing to it. Yeah, that's correct. And then there is also an answer. Hassan says the extent of randomness, which is also very correct. Yeah, so again, the length of data somehow is relevant to that. So we can actually go through some reasons. Again, this is not the comprehensive sort of list that we talk about here. I will put also one chapter from our book that is very relevant to this discussion called Why Does Forecasting Fail? So in that chapter, we discuss a couple of reasons relevant to the discussion we have here. So here are some reasons why something is easier to forecast. So you mentioned, I think, at least I saw a couple of answers talking about and influencing factors or causal factors. So it is very important. So for the forecast variable, there are always, different factors or different predictors or different variables somehow influencing it. So if you have a good understanding of those factors contributing to the variations of the variable that you want to forecast, well, there is a chance that we can also build a model based on this and then produce good forecast. Now, the problem is if we have an understanding of factors, but then we don't have any data for it, then it wouldn't be even possible. So understanding factors alone is not enough. Hopefully, we have a good understanding. And then we have also a lot of data available for this. And I think yesterday there was a question about how much data we need for forecasting. There is no definite answer to how much data you need. Of course, most forecasting models, they need a sort of like a minimum length of time series to produce a forecast, but there is no limit on the maximum. It seems like if we talk about the time series data, more data in general is better. Because in particular, if we focus on probabilistic forecast, so more time historical data is better. So these are two main factors, and most of you highlighted these factors in the chat as well. Now, there are some other factors that could also make something easy or difficult to forecast. So now, if you produce a forecast and that forecast cannot affect itself, like the thing that you forecast cannot affect itself, there is a chance we could also get a good forecast. Now, this was actually the case during COVID-19, right? So let's say countries, they produce the forecast of COVID-19 related variables like positive cases or death toll or similar variables. And then based on these variables, they make a policy or decisions about what to do. For instance, they introduce lockdowns, right? So, and because of that, now what happened in the future was maybe different from actually what we forecast. And that is, well, in the case of COVID, it is fine because the idea of the forecast in this case is not, to be accurate, but it is to influence a policy and trigger actually decisions that matters. But COVID is an example of this. So we forecast something and then that affects somehow the actual values in the future. But currency rate forecast also could be similar. So let's say if you forecast that the currency rate increases for something, that changes the behavior of people, and that will affect the actual exchange rate in the future as well. So again, you need to think about this, whether the thing that you forecast will affect itself or not. I think there was at least one answer in the chat as well about randomness. So in general, if you are dealing with a time series that has low randomness or low unexplainable random variation, or what I call also irreducible error, then there is a chance also you can produce a good forecast. So if, again, this goes back also to that entropy metric that we introduced earlier. So if you have, let's say, strong signals like trend and seasonality, autocorrelation, let's say, and there is less randomness, so you have strong systematic information, and that is very good to produce forecast with. And then the last point is about, again, the example that I showed you, if the future is somehow similar to the past. So you need just to make sure we understand this point, because here we don't mean that the future repeats exactly like past. I think what matters here is the systematic information, okay? If we observe strong seasonality in the past, we also assume that we will have seasonality in the future, right? If this is not happening, again, if you think about the example I showed you earlier with tourism visitors to Australia, and after COVID and before COVID, you clearly see that the future is not similar to the past, and that's why the forecasting model that we use in that case failed as well. So to summarize this, these are some factors to think about when you are dealing with the forecasting problem. I think it is important to think about them before start, the journey of building models and going through the rest of the process. And this is actually what we are trying to do here. So far, I was trying just to, first of all, give a definition of the forecast and make sure we are all on the same page in terms of what we mean by a forecast. So just to summarize, when we talk about the forecast, we refer a forecast as a probability distribution, and then from there, we can extract any information that we want. So when we talk about the probabilistic forecasting, we can visualize it in two different ways. One of them is through the trajectories or the future path, and another one is through histograms or density plots that you saw, and we will learn how to do it later. And then following that, we also discuss different factors that affect the forecastability of a variable. So forecastability here refers to how easy or difficult a time series is to forecast, and we look at the different factors that affect that. Now, for the rest of this session, we are actually looking at some simple forecasting method first, and then we learn how to specify or estimate forecasting models in Fable in general, but we show you here with these simple examples, and then we learn how to produce a forecast, and then later discuss what actually we mean by fitted value and residuals. So here is a time series that you have seen before. So if you think about this time series, and if you want to use a forecasting model, what forecasting model would you use for this? And because we haven't maybe covered the forecasting models yet, if you have, let's say, a way to forecast this time series, what you want to capture from this time series. So it seems like we have some consistent pattern within that fixed period of time, which is what we define as seasonality. Yeah, and as you said, yeah, so if we have a method, we want to make sure that method could somehow project those consistent patterns that we observe in the past into the future. And there is a method that can actually do this for us. This one, number of pigs sluggered in Victoria, is the yearly time series. So you have year in x-axis and y in, and thousands of number of pigs sluggered in y-axis. This one might be a bit challenging because it seems like there is no, at least, visually, because sometimes we cannot also for sure say visually what is there. Sometimes as human, when we look at the time series, our eyes try to find patterns when they don't exist. But it seems like there is no obvious, consistent pattern that repeats. I don't know, you may see that there is a bit of like a line that goes like this, a bit of increasing trend there. And maybe there are different things that also affect that. So it seems like there is some similarities in certain patterns. So there could be also some cycle, for instance. So you need maybe a method also that captures if there is a trend there, but I don't see any seasonality. There might be a cycle because there's a yearly time series as well. And this one is a Facebook closing stock price in 1 year, 2018. Again, if you look at this, you may see, well, there is up and downs, and you may see this is also there is a trend that changes direction, and if you have a model that captures this, then you can use it to forecast the Facebook closing price, let's say for next day or so. But for those of you work in, let's say, finance, or you deal with financial time series, in particular with the stock market, you know that it is quite challenging to forecast this because there are a lot of things that we don't know. And that's why actually sometimes to forecast something like this, a very simple method could be very effective. So here I introduce some simple forecasting methods, and we call them benchmarks, right? Now, one question is, why do we need benchmarks? Why do we need simple forecasting methods? Can you think about this for a few seconds? Why do we need benchmarks in forecasting? Or do you need to have benchmarks at all? Benchmarks are the worst case scenario. No, I don't think they are worst case scenario, but again, you might mean something different by worst case scenario. Yeah, so I think Agnes, if your name, I pronounce your name correctly, so I think you mentioned, well, I lost you. There are more comments. Yeah, and compare with complex models. Yeah, I think that's a good answer to find the base level for comparison. as a starting point. They make a basis for forecasting, yeah. I think this is actually very important. As a principle in forecasting, you need to always have a benchmark in your toolbox, regardless of what method you use. You need to have something as benchmark. So the benchmark could be a very simple models, like the one that I will go through them in a second, or they could be an existing model in your domain. Again, if you work for a company, you may have already a model that is used in the company, or if you work in a certain, let's say, field, there might be models that are known to be reliable in that area. So again, as you see, the definition of a benchmark could be different, but it means you have something to compare against. So it is either an established thing in the area or an extremely simple one. We always recommend to include an extremely simple method in the toolbox. And for two reasons. One, sometimes, surprisingly, these extremely simple methods are doing a good job. And sometimes, so they are good. The second reason is whatever investment you put to build a model that is more complex than this simple model, you should be able to justify that. And the justification here is by the benefit that you get from the new or more complex forecasting model. And one way to do this is to evaluate the accuracy of the model, but there are, of course, other things as well. Like you can look at the computational time, for instance. You can look at the explainability of the model. So there might be other criteria when it comes to evaluate the quality, but accuracy is one of them. All right. So we need benchmarks. Remember this always as a principle to include it in the toolbox. So here we look at some very simple ones. The first one is called total average. Now we are introducing some functions also in Fable, right? So for every forecasting method that we introduce from now on, we have one function in Fable. So as you know, functions also are names, and you need also to note that all the forecasting models in Fable, they are in capital letters, okay? All forecasting models that you will see later, they are in capital letters. So here for the total average, the function that we use is mean. And then of course, all functions followed by parentheses and then the arguments inside the parentheses. So now what total average does is, it takes all the observation that we have in the past, it averages them, and then it uses that as a future value, or what we call the forecast. So here is the mathematical representation of it. Okay, so the total average takes everything, divide by number of observation, and use it as a forecast. Another simple method is called naive. So the function name in Fable is naive in capital letters. So naive is very simple. It looks at your time series and it takes the last observation in the time series and use it as a forecast for the future. So as you can see here, the forecast for the future is a constant number. And then here is the constant number as well. So it just assumes the future is exactly the same as the last observation. And actually this is quite good for the sort of time series we saw, like Facebook closing index, but in general in financial market. Another simple forecasting method is called seasonal naive. Again, similar to naive, but the difference is instead of looking at the previous observation, we look at the previous season and then we repeat that. Well, what we mean by season here depends on the granularity of the time series. So if you have monthly time series, and if I want to forecast for January 2025, I look at 12 months before, which is January 2024. If I want to forecast for February 2025, I look at the value of the time series in February 2024 and so on, right? So we look at the previous season, and then depending on the horizon that you have, you may want to repeat that. And then finally, we have also another method called drift method. So this takes the last observation and then it takes the average of the changes in the past. So here there's the difference between the consecutive observations, and then this is the average, the total number -1, because we start from the period 2, and then H is the horizon that we mentioned as well. We could do some simple math to simplify this part. So if we do that, then we will have something like this. So drift basically is the last observation plus the last observation minus the first observation divided by the length multiplied by H. So this is like, you know, a straight line, you know, that goes from the first observation to the last observation, and it continues on. So it is something like, you know, what we see here. So remember, the function for the drift method is RW. This is for random walk. So it takes the name of the variable or the column that you want to forecast, and then you have a tilde, and I will talk about this in a minute. So if you have this tilde, it means you can add more, you know, components or specific functions or sometimes variables from the data to build your model. So for now, you just need to understand how these simple methods work and what are the corresponding functions in Fable. Okay, now this is possibly one of the most important part of this session. So please, you know, take notes, because we're going to repeat and use these functions more and more. So now the question is, we introduced some simple methods so far in as benchmark, but as I said, we add more and more to this now tomorrow and this after in the next section as well. So remember, for each forecasting model in Fable, you have a name. This name is in capital letter. Now, how we should specify them, how we should write them when you want to build a model. So there is a like a system that we introduce how to do it now. So model specification in Fable supports a formula base. So again, for those of you are familiar with base R and you have maybe used regression there, you know that when you want to write a regression model using LM, for instance, you need to write a formula. So how we write this formula in R, or how we express it, is using this. So basically, when you write the formula in left-hand side, we have what we call the response. This is the column from Tessable that you want to use for your forecasting. So basically, this is the variable of interest for you to forecast. This is what we call as a response. And then you have a tilde after the response. And after the tilde, we have terms. And what are these terms? Well, these terms could be some specific functions that are specific to each forecasting model, and we learn some of them, but they could be also the predictors from, you know, the data that you have. Let's say if you forecast the demand and you have temperature, well, the temperature could be used as a term there. All right, so remember this. In the left-hand side, we have the variable you want to forecast, and in the right-hand side of the tilde, you have the terms that you want to use to build that model. Again, as a reminder, remember all forecasting models in Fable are in capital letters, like seasonal naive here. Okay, now, how we write this? Basically, this is a template that you can use for this. So remember, to do the modeling using Fable, we need to have a tissable. So we learned in the past 2 days how we create a tissable and how we use it. All right. So if you have, I don't know, a data frame or a table, you need to make sure first you convert it to a tissable. So once we have a tissable, we use the pipe. So we take the tissable, then we pass it to a function called model. So this model function, it trains the forecasting models on the data. And by training here, we mean it estimates the parameters of the model, calculates fitted values, and so on. Even residuals and so on. We will see the components of this later. But for now, just let's learn how we specify these models here. All right. So take a tissable, then pass it to model. Inside the model function, we can have a list of forecasting models. Now, the first thing that we start with is the name that you choose. Okay. The thing is, and I will show you later when I do some live coding, if you don't provide this name, so the function takes this as a name of the column. Okay. So this name goes to the column name, and it makes it easier for you to analyze later if you like. So if you provide a name of your choice and then equal, here you provide the function name like snaive, like mean, like naive, etc. So provide the function name in Fable, and then inside the parentheses you provide response, tilde, and then terms. Now, if you have multiple terms, you add them using a plus. So the first term plus the second term plus the third term, etc. And then remember, these terms, the easiest thing to imagine is the variables or predictors or columns from your tissable. Okay, so you can add them using a plus. Now, sometimes you will see later, we have only a response and not any, not tilde in any term. Actually, if you see that, it means, well, you don't use, first of all, any other predictor from the data in this model. And then if you don't provide anything, either that model doesn't have any specific function, or you just use the default value of it. Okay, so you don't bother with going and look at the specific function of things to specify things. You just trust the algorithm and you use the default values. So this is basically a template of how we fit the models in Fable, how we specify the methods first. This is how we specify methods, and then this is basically how we fit models. This is how we train these models using model function on this data. And of course, we pass this to a name. And with this, we call this name a model table or Mabel. So here's an example. So we use aus production, which is the data set that is available in FPP3. We pass it using a pipe operator. I think some of you also asked yesterday why there is two different type of pipe operators. Here there is one, and here a new one. I will show you in a way how to change it. This is called a native pipe operator. You can, depending on your RStudio version, you can change this. And this is a pipe operator from a package. I recommend you to change it to this if you can. So we take our testable data, we pass it to the model function, and then here I specify some names. Here is my seasonal naive method, random walk, and mean. And then inside parentheses, I provide one column from that aus production that I want to forecast. And then remember, I use this comma to separate each model, right? So when I specify one model and then I go to the next one, I put a comma there, okay? Now, when you run this and you run the entire thing, or you run this, and then of course, using this assignment, you put this result inside the beer fit, And if you run this, this is actually the output of this. And this is what we call it a model table, right? Or simply a Mabel. Now, what is in a model table or Mabel? In a model table, you see each column corresponds to one forecasting model. Okay, each column in Mabel corresponds to one forecasting model. Here we have 4 models and we get 4 columns. What about rows? Each row corresponds to one time series. Here, I have only one time series, I get 1 rows. But later, in your exercises, but some other examples maybe, you will see multiple rows. If you see multiple rows, it means these models are fit to many time series, more than one. So this is one thing you need also to know. Now, another question you may ask is, okay, what are this thing inside this? Well, these are information about the model fitting. And then I show you some functions, how to extract the information inside each of this to understand how these models are fit, what are the parameters, and so on. But actually, we don't see much information for simple models. This afternoon or tomorrow, the next section or tomorrow, when we talk about exponential smoothing and ARIMA, I will show you how to extract this information. This is where we see more interesting information. But here are some functions to note. So one of them is called report or tidy or glance. So this functions, you take your model table and you pass it to these functions, and it will somehow unpack what is inside, those secret sort of names. So it unreveals the information inside. And for now, you can just actually note these functions. So simply these functions can reveal the information about model fitting, and sometimes you may need to look at them and understand them, or may extract information for any sort of purpose there. So these are the functions that may help you to do it. Now, once we fit the model, of course, we can look at the performance and how good this model is. And there are 2 ways to look at this. One is to look at how good the fitting is, how good the model that we use fit the data. But another thing that we need to look at is how good the model is to forecast the future data, right? These are 2 different things. And this is the topic of Friday. So on Friday, we specifically look at this the whole day. We discuss how we check the model performance. So I skip this for now. So the next thing that we do is to produce the forecast. All right. So far we took the testable, we passed it to model, we specified the models, and then we trained the model. But training is not enough. We need to forecast also. How we do it? Well, the forecasting is done using a function called forecast. So this function takes the model table, which we just created. So we take this, we pass it to forecast function, and inside this function, we have to provide an argument called h. And you remember what h represents? It represents the forecast horizon. So h could be a number like 1, 2, 3, right? And this, for instance, if I want to forecast for the next 3 periods, I can put h equal to 3. But also we can represent this with as a natural language, like 3 years, right? I typically go for the number, but because that number matches also the index that we have in testable. So let's say if my index is a daily, when I say h equal to 3, I mean 3 days. If my index is monthly, then when I say h equal to 3, I mean 3 months. So automatically it matches there. But you can also use natural language if you want. Now, there is one specific case. If we use models like regression, and if we use some dynamic regression, like using ARIMA function that we cover tomorrow, you may have predictors. If you have predictors in your model, again, this is a slightly a more complicated thing, but if you have predictors, you may need to include the forecast of those predictors in your model as well. So if that is the case, instead of providing H as a number, actually you have to provide a data set of the future time periods for those predictors. Let's say if I have temperature and I use the temperature as a predictor to forecast the sales of today, and if I want to forecast the sales of tomorrow, I need to provide the forecast of temperature in this argument, right? So we will see that in the exercises that we provided as well. All right, how we do it, remember, this is the model table, the one that I created here, okay? So again, my testable, pass it to model, and then the list of models, and I assign it to this name. So this name is my model table. Now to create a forecast, I take this, and then I pass this to the forecast function. And then here inside, I say H equal 5 years. And then this is quarterly. When I say 5 years, this H automatically becomes 5 multiplied by 4. So it is actually H is equal to 20 quarters. So this is here is using natural language with 5 years, but it means 5 times index, which is the quarter. So it means 20, H is equal 20 periods. So the output of this, so if I do this and pass it to this and run it and assign this to this name, and then if I check this name, then I see actually this table. This is called fable or forecast table. So this is also, the structure of this is a bit similar to the testable. Okay, we have here the index that says we have a quarterly data. Now you have the key here because our key here is created automatically. This is different from, we didn't specify it. You know, in testable, we have to specify key because it is a data. But when you pass it to fable, depending on the keys that we have in testable and number of models, it will create this as well. Here I have one time series, but because I have 4 different models, then my key becomes .model 4 here. So what we see in the table, well, we have a column called .model. This is the list of models. And then we have an index that corresponds to this index we have in testable. So this is the same name, quarter. And then we have now 2 more columns. One of them is the forecast distribution. Okay, and this is what you see here as this as a distribution. And the name appears as the name of the variable, basically, that you forecast. So this is the same name that you see in the data as well. So this actually is only normally the normal distribution. So the distribution is normal distribution. Here you have the mean, and here you have the variance of normal distribution. And then, as you can see, that mean here means the point forecast. Okay, so it means the mean of this distribution, as you can see them here. So remember, the column that mean means simply a point forecast. And then that distribution then contains the entire distribution. And we could now have any information from this being extracted, like prediction intervals, quantiles, or the entire distribution to be visualized. Now, when it comes to visualization, it is actually pretty straightforward. It's very similar to the sort of visualization we have seen before. So here, first, we take the fable or forecast table, we pass it to autoplot. Now, if you want also to include the previous data or the historical data, so you need to include them there. But if you don't include this and you just have the data, you will just see the forecast, not the data. So I think it is nice actually to see the data as well. And then here we put level argument of the output equal to null, because we don't want to see prediction intervals for all these 4 models. And then, of course, we will add some more information to this. This is somehow related to ggplot2, so we can also add more if you like. Now, if you look at this forecast produced by these 4 models, visually, it seems like the only model that somehow is capturing the information that we see in the past is seasonal naive. But this is basically not a good way to evaluate the forecast accuracy. Okay, visually, we cannot rely on just visual representation to see, oh yeah, seasonal naive is a good one. So there is a reliable or solid, let's say, procedure to follow to make sure the forecast has been evaluated and captures all the systematic information. And then this is something, again, we cover on Friday. So coming back to the forecast distribution, so the forecast distribution is what we are interested here. And then again, remember, often when people talk about forecast, they mean just one moment of that distribution, which is typically mean. It could be also the median. So from now on, we need to make sure we distinguish 2 things. When people talk about forecast, we need to see if it is actually the point, if it's the distribution, or it is the prediction interval. It could be different representation of this. So in Fable, we can create probabilistic forecast using normally distribution. There are some additional packages that could also be added to get a distribution like Poisson or negative binomial, but for now, the primary focus is on normal distribution, but also a non-parametric approach like sampling, which is called bootstrapping, that is also implemented in Fable. Now, for simple models that we cover here, this is how the distribution basically is produced for the forecast period. So assuming the residuals, I will talk about residuals in a minute if you're not sure what it means, but basically the residual simply is the difference between what we call the fitted value and actuals. So assuming that the residuals are normal, they are uncorrelated, and the variance of the residual is constant. So it means it doesn't, grow, like this. There is a term that I can't pronounce correctly, but it means basically the variance somehow is constant, is within the line if you plot the residuals there. Now, so remember, this means we want to forecast for period t plus h, given that we have information from the beginning of the time series until the last period, which is called t. So given these assumptions, now we have a normal distribution. So this is the mean, and then we have the variance of that normal distribution. So as you can see, for instance, the first one, which is mean, doesn't depend on h at all, right? It just depends on that the variance. So here it depends on h. So it is increasing actually with h. So here it depends on h as well, because that k is the integer part of h minus 1 divided by m, and m here is the length of seasonality. If we have a tissable that is monthly, m is 12. If we have a tissable that is quarterly, m is 4 in this case, right? So again, this is the analytical or the mathematical representation of the distribution that we see later in Fable package that is implemented there. Now, if the normal distribution assumption for the residuals is not reasonable, we can use another alternative called bootstrapping. And this has been implemented in Fable as well. So in bootstrapping is a sampling technique. So basically what happens is we produce a forecast, let's say for the next period, and then now we go and sample from the residuals. And then remember, the residuals are from the trained. It is in the past, is not about the future. right? So we sample from that and we add it to the point forecast. And we repeat this multiple times, 1,000 times, let's say. And then for each period, we get 1,000 possible future. And this is how we go for that, different future path that I show at the beginning. Actually, that was created using a bootstrapping technique, which is simply a sampling from residuals, adding it to a point forecast that we create. Now, if you want to generate the bootstrapping, so there is a function for it in Fable as well. So this is the same house production, but just filter actually the index to be just 1 year. And then inside house production, there are many variables. We just look at one of them, which is beer. And then we pass it to the model, and then using just naive. And then now we pass, this is our Mabel model table. We pass it to a function called generate. This is our horizon. And then now there is an argument called bootstrap. So bootstrap is true. It means we're using bootstrapping. And then here you have an argument called times. It means how many times we want to repeat this, right? So remember also this function, but if you want to use the forecast function, this is basically the output of this. So you just plot it. So you have this 5 different future paths because I generated 5 different future paths using the generate function. But another option is you can actually use bootstrapping directly in the forecast function. So if you don't provide the bootstrap equal true here, you wouldn't get any bootstrapping. You just use the normal distribution to produce the distribution. But if you have bootstrap equal true, then you will get the forecasts that are generated using bootstrapping. And then here, basically, you in the distribution column, you just get the sample. And by default, it generates 5,000 different paths. So again, this is another way to use bootstrapping here. You can extract prediction intervals using a function called hilo and provide, the coverage of prediction interval, 90, 95%, whatever level you want there. And then you can also unpack hilo, let's say, to separate columns for lower bound and upper bound in the prediction interval. So you can also provide multiple levels if you want simultaneously. So you get a 50% prediction interval and 75%. And if you want to unpack them, so this time you have to use a mutate function, which is from dplyr, and then you can have the lower bound and upper bound. You can have the name of the function inside like tick boxes, backticks, sorry. So inside the backticks, and then using the $sign to extract the lower and the upper. So this is another way to separate the lower bound and upper bound for each level that you want. Okay, so the fitted values and residuals is something that I will cover on Friday as well, but just simply highlighting fitted values actually is one step ahead forecast and is corresponding to the training data. Okay, when we talk about fitted value, it means for each value, each data point that we have in the data that we use for training, we get one estimation of it. And then what happens, it depends on the model, but what happens typically is we go to the beginning of the time series, and then we start saying, okay, now for the first period, how I can produce an estimate of the actual. Now, after period 1, I say, okay, how I can estimate a value for period 2. And then you actually keep doing this until the last observation. And by doing this, we create what we call a fitted value. So fitted values are one step ahead forecast. This is why this is different from forecasts. Forecasts are typically multiple step ahead forecasts. But also when we generate forecasts are for the future. And then we don't use all the data to generate the forecast when it comes to evaluation. But I covered this on Friday. Okay, so now, because I will go through this and I know that I don't have much time, I think what I want to do is I just want to show you one example of, let's say, how we do this. So let's take, well, first of all, I need my libraries because, so FPP3. And so let's say I take aus production. So this is actually the one that I have from Tissable, right? So this contains, again, is a Tissable, is a quarterly one, but it contains an index, which is quarter, and then there are many different productions. So if you want to know actually what is the aus production, so you can also look at the help file here. So it gives you information about what this data set contains. So what I want actually to focus on here is just one variable. Let's say I select my column to be just beer, right? So by doing this, now I have only one time series. And I just give this a name called aus beer. And I think I told you there was, yeah, so if you go to tools, and global option, and then if you go to code, do you see there is one option here called use native pipe operator? So if you tick this box and then click on apply and OK, right? So you will get this pipe operator here instead of the one with percentages. Okay, this is something I think one of you asked there. And then if you want the short key for this pipe operator is Command Shift and M. Command Shift M in Mac and is Control Shift and M in Windows. Okay, Control Shift M and Command Shift M. All right, so now I have my data. So what I do is I take this and then I will filter some part of this actually data. You can actually filter this data using a function called filter index. This is from Tissable. So this is really a good function if you want to filter the index part of your Tissable. If you want to know more about this, again, check the help file of this. There are detailed information about how we do it. Now, I want actually to filter this from the beginning. So that's why I put a point and then I put a tilde here until, let's say, 2009 and quarter one. Well, you can change this. This will give you about 213 observation, and the rest of this would be used later for plotting or creating forecasts. So I filtered this part, and then I pass this to the model function. Let's say I start with just one model called seasonal naive. So I give it a name. Remember, this is my name. You couldn't represent this in different way. I just call it S name. But then after the equal, I have to provide the function that corresponds to the forecasting model called S naive. And then inside this, I will provide, okay, what is the name of the column from my data, which I want to use for forecasting, or my response variable. In this case, is beer. So you can just type it or paste it here. Okay, so if I do this, and then if I run, now I get actually a model table with one column and one row. Why? Because I have only one model and then one time series. Remember, this is only one time series. There is no key here. Okay, so I can now put this in a name called fit. And then I can actually have this fit and then pass it, sorry, this should be this, pass it to the forecast function. And then this forecast function is h equal to 5 because actually the 5 is remaining, if you like, from the whole. But again, this is something you could change later. It's just for demonstration here. So if I do this, now I get basically the fable or forecast table for 1, 2, 3, and 4 columns with the distribution, and then with the name of the model, because I have one model that is just that, and then 5 horizon, 1, 2, 3, 4, and 5. So remember, this becomes very complicated when you have actually a lot of data or a lot of time series, let's say there. So I just give this also a name, FCST. And then that's it. Now, I want to do something. I want to actually visualize the distributions here. Okay, now to visualize the distribution, I'm going to use another package here called ggdist. Okay, so if you don't have this, you can install it, and I will share the code later as well. So you can install, you can use the code and create the visualization as well. So I do this first with the ggplot, right? So my ggplot and the data that I have here is basically my table. And then, of course, I need my mappings here. And then the aesthetics. So here, what I want to put in x-axis, well, is actually the quarter. All right. I want to have the quarters in x-axis. And what I want to put in y-axis, well, I want to put the distribution, which is this column. Now, because I'm using this ggdist, instead of typical y equal, I have to put y dist. This is from this ggdist, and then I simply put this here. So if I just run this, so I just get this blank surface there, but I need to add a type of plot that I want here. So you can use different actually type. The one that I use, and I just type this ggdist here, just to tell you this function that I use is from ggdist. It's called stat underscore half I. Okay. There are many other functions. I strongly recommend you to check out this ggdist. There are plenty of interesting functions there. So if I just run this, I get actually the distributions for the 5 periods. So here you have the distributions. And this is quite nice because it's normal distribution. You can see the shape of it. And then the point actually here is median. You can also change it in this function if you like to be mean. And then you have 2 intervals. You see the thin and the thick line. So these are the prediction intervals. So one of them is 95%, and another one I think is 66 by default, but you could also change those 2 things that you can see. So by simply by just doing this, you can add, the distribution. Now you could actually do more things if you like, but I will simply actually add things here because I know I am almost done with the session. I will share. I have already completed this. So what I do is I will just add this here. So basically what I want to do now, instead of just seeing the forecast as we see them here, I want to have a bit of historical data and then also a fitted line there, and then just represent the distribution in a bit like a nicer way as well. So I need to do a couple of additional things. I just actually put them here. So I need first to use this function called augment. So if actually use augment, so in the augment function helps you, this is one of the functions that helps you to unpack actually what is inside the model table. So it gives you the fitted values and residuals. Okay. So for now you can ignore these 2 things. For now they are the same, but in some cases the .inov and .resit could be different. But this is the fitted value, this is the actual, and these are the difference between these columns, the difference between the fitted value and residual and actuals. So I extracted the fitted value from here, but for the rest of this, so I will present this actually. So there is a bit of ggplot thing actually to do, so it is not related to forecasting. So I just put the entire thing here, and then if I just make it a bit like this, now basically you have your fitted values. Again, you could use different colors for this if you like. So this is the fitted value. The blue line is the data, the actuals. And then this is the point forecast and the distributions. And you can see also how the actuals, which is the blue line, is within, some bounds, or how close it is to the point forecast as well. So the idea is to produce the forecast, but also to visualize it. Sometimes you may need actually to do this because people if you publish, sometimes you need to show this. If you work for an organization, people may ask you to visualize them and send them the sort of like forecast you produce. So I think this is a nice way to do it. So, what we see here is the core part of what we have been doing. Okay, so make sure, first of all, you know how to create a testable. Once we have a testable, of course, you can filter or not. This is something I did, but if you don't do it, still you can do forecasting with this data. If you want to add more models to this, you just basically put a comma and then press enter, go to the next line, and then add, more models. So I just add basically naive here, and then I will add also average, let's say, call it average. So you see this name is for me. And then this is mean. All right, so here we go. So if you do this now, you see I have more columns, but still the same one row. But the rest of this would be similar. Okay. Now I wouldn't plot this because, having the distribution and all this information for a couple of different methods would be a bit more complicated, but you could also have actually different distributions here if you like. So that is possible. So this is basically what we need to know for now. How we add things there. And then how we produce a forecast, and then we can extract information from it as well. And if you want to visualize the forecast, this is one way to do it. If you want just to visualize the point forecast, so it is easier, you can simply use autoplot, and autoplot will produce the plot of the forecast for you as well there. All right. Is there any question before we go for a 10-15 minutes break? So there are 9 questions here, I see. Okay, let me stop for this. So there are a couple of questions here. Is there one ideal H window for forecasting year data? Like, can you forecast for more than 5 years? So the forecast horizon depends on the decisions that you want to support. So remember, in the forecasting workflow, at the beginning, we have to decide why we use a forecast for, and then that should dictate, of course, the horizon. Now, of course, if you want to forecast for 5 years, it depends on the time granularity that you have, right? If you have 10 years of data and 10 years of monthly data, and you want to forecast for 5 years, well, still, yeah, of course, it is possible, but then maybe it wouldn't be easy to evaluate the accuracy and everything else. So if you have more data, yes. So there is no definitive answer to this. It depends really on the objective the purpose of forecasting, but also the data availability, how long the horizon is. Well, is public health, what can we forecast? So I don't know what you mean by public health there, but because there are plenty of things you can forecast in public health. For instance, there are forecast variables in public health that you can actually predict, like mortality, fertility. These are the variables where we have a lot of data, and actually I have seen models even forecasting for very long term, like 2050. So quite, long term into the future. But you can forecast a lot of disease. Also, you can forecast, for instance, the pharmaceutical items, health commodities, and this sort of thing. Again, remember, if we talk about in public health, what can we forecast is, well, we have to think about the factors. And then I don't have deep knowledge of public health, but these are some examples that, of course, I'm aware of, but there might be more there. I don't know, when you said last point, did you mean, Gabriel, did you mean the last point in the, I suppose you were talking about the slide where we have what easy or difficult to forecast? I'm not sure if that's what you mean, but in one sort of assumptions we have in time series forecasting is we have a past and we have a future. So the assumption that we have in time series forecasting is the future is similar to past. In what way? The sort of systematic information we observe in the past, we assume we observe them in the future as well. Again, remember the slide I show you with the tourism visits. Up to January 2020, we have certain systematic information, and it was consistent over time. We observed them, it was always similar. But then when COVID happened, it was not similar anymore. The actual drop to zero, but the model assumes that still we have those consistent patterns. So that's what we mean by similarity between past and the future. So the probability distribution, so there are assumptions around this. So actually Mitch is developing a package called distributional. Is it distributional, Mitch, if I'm not wrong? So there are plenty of...
Yes, it's distributional.
Yeah, there are plenty of actually distributions available there. When it comes to forecasting, as I said, either you have some assumptions, like normality, for instance, and based on that, we have a normal distribution, but you could also have assumptions like Poisson or negative binomial, and then estimate the parameters of those distribution and then use them for forecasting the future. But if not, then you could use other techniques like the one that we have here, like bootstrapping. These are two main things at the moment covered in Fable, so normal distribution, and if you believe that the assumptions of normal distributions are not valid, you can use bootstrapping. So
another very common thing that we have with distributions and forecasting. Yesterday we talked about transformations, and I also mentioned how we back transform the data when we produce forecasts, and that happens automatically. Then you'll get a transformed normal distribution instead of a normal distribution. And that can have a long tail, it'll be non-negative. There's a different set of features associated with transformed forecast distributions.
All right, so what is Fable? Fable is a forecast table. So again, I hope that answered the question, because I showed you the table and then what we see basically there in the, well, I can very quickly just share the slide and so basically this is the forecast table that we have here. Where is that? Yeah. Okay, this is the Fable, a forecast table. So it contains the list of models, the index or the future periods that you want to forecast, or the periods that are included in the forecast, then a name that you forecast that has a distribution of the forecast, and then the dot mean, which is the point forecast, basically for that model and that period, right? And that variable, of course. So that is the fable. Which benchmark is the best? There is no best benchmark, really. The ones that we cover here, they could always be used, but it depends on the context, the domain that you're working on. You may have some, well-known models in your domain, so you can always use them. If you don't have any, you can always use one of these models like seasonal naive or naive. So that is, I think, answer to this question. Please, how to get access of data to those models? I'm not sure actually what the question means, but is the training of the model, do we split the data? We discussed about the splitting the data on Friday. So at the moment, as I said, we just want to highlight how we specify a model, how we train a model, and how we forecast in Fable. But the procedure of splitting the data, why we need to do it, etc., this is something we cover on Friday. Yeah, so this is a good question. Where do we get the data for future observations? So again, this depends on the context. For instance, assuming you use a population, okay, population as a predictor in your model. So if you use population, you could generate the forecast yourself, if you like, build a model to produce population. But, there are some organizations, they do this job. They're very good actually in doing it. Like Office for National Statistics in the UK, they do this job. So they focus on, producing forecasts for population. So you can get it from there. Sometimes it's publicly available. If you forecast, let's say, something and you use weather, or temperature, let's say temperature as a forecast predictor. So you may actually find this forecast generated by Met Office. I think they are not maybe available for free, or maybe they are available, so you have to check. So you can get the forecast from Met Office. Sometimes actually you need to pay maybe for that. So this is somehow you get the data for these predictors. So again, it depends on the context. It might be available, is available somewhere, you can get it. If not, you have to do it yourself. So when you said, are the models you show the default for benchmarking and forecasting? Again, these are typically what, we use here, but, it depends. For instance, if, if I forecast in, let's say, hospitals, and I do emergency department, right? So emergency department forecasting is typically a daily time series or hourly time series. And I know that, for instance, for something like that, mean wouldn't be a good benchmark, because I have multiple seasonalities. So I need maybe to create a simpler benchmark, maybe that takes within day and within week benchmark, somehow combine a sort of seasonal naive that we have, but then have it for both daily and weekly. So it is still simple, but it is not exactly seasonal naive. It's a combination of two types of seasonality. So that's why as I said, benchmark depends on the context. But if you don't have any sort of benchmark in your domain, or if you don't know, then you can always use one of this seasonal naive, or mean. How do the models handle outliers? Well, I mean, this is not something that we cover here. These models, they do not deal with outliers. Actually, this is something Mitch, I think, will talk about in a minute after this. Well, after this session, Mitch will actually do an example, I think, or all it will tell you how to do it, maybe with dummy variables. Yeah, so among the four models, how do we determine the most appropriate one? Again, this is a topic of Friday. So on Friday, we just talk about this. So given a toolbox of forecasting models, how we determine which one is more reliable, most accurate. So we discuss a procedure for that. We calculate things, we visualize things, and we summarize things, and that helps us to make a decision there. In the model function, which variable should be included as a response, as a predicted terms? So when it comes to a model function, so the response is always one variable, okay? The response variable is the column from the tissable that you want to forecast, okay? So remember, you have a tissable, your data, there is only one column from there that could be the response variable. So the response variable is the variable or the column from the tissable that you want to forecast. And the rest of the terms, again, they must be in your tissable. So somehow you add those categorical or any other predictor, they must be a part of it. And you could add them as a term after the tilde with a plus as well if you have multiple of them. Yeah, why does this column produce these two columns? Well, again, you might be familiar with the select function from dplyr. Yeah, typically if you use select function and you say select beer, then it will just select the column beer. But here, because we have a tissable, right? And a tissable doesn't mean anything without an index. So whenever you select something with a tissable, automatically it includes also the index there. So that's why here we have basically aus production, which has the index, which is quarter, and multiple names. So here I just wanted to focus on beer. That's why I select beer, but the quarter, which is the index, will be also automatically selected there. So for time series data, the term is time. Well, the term, again, we cover a couple of them now in the next session, but tomorrow as well, there could be different things. The time could be one of them, but the time somehow is actually embedded in the in some specific functions. So in the regression, we talk about them, but the term is, again, some specific functions like trend, like seasonality, for instance. These are a specific function, but again, the term could be an external variable as well, like temperature, like population, those sort of, like, I don't know, a strike, for instance, in a data. If there is a strike in a day, these are dummy variables. So this could be different terms there as well. I think we are done with questions. So shall we have like a short break, 5 minutes, and then we are back for the next session?
I think that's a great idea.
Sorry, I'll pause maybe this.
Resume screen sharing. Excellent.
Yep.
And I see a couple of people have successfully put the code in the chat, so I appreciate that. Thank you very much. Okay, our second topic today is one that you're probably already familiar with it, but you perhaps haven't used this before for time series forecasting. This is, of course, regression. So yesterday in the last session, we learnt about localized regression, and when I asked a few questions about that, you all seemed quite familiar with regression. So hopefully this topic won't be too challenging for you, but it will give you a good idea for how we can overcome some of the problems with the benchmark models. So if you recall from Bahman's session just prior, the simple benchmark methods were able to capture trend with the random walk with drift method. It was able to capture seasonality using the seasonal naive model. It was able to capture a lack of trend and lack of seasonality using a naive or a mean method, depending on how the data worked. But there weren't any methods that could capture both trend and seasonality at the same time. And for all of the models that we'll see for the rest of this workshop throughout the week, these models will be hopefully better for many applications and many problems for forecasting compared to the benchmarks. But we have to start with the basics. We have to learn about our benchmarks in order to evaluate which model is better. And of course, the more complex model that you're using, hopefully that can do at least as good as the simple benchmarks. And that's more difficult than you might expect. It's really hard to do better than the naive or the seasonal naive forecast. And that's why they're used as benchmarks to make sure you don't present something really advanced and complicated that isn't as good as just copying the day yesterday and using that as your forecast. And you'll find it surprising how often it's better to just do that. The other thing that regression allows you to do, of course, is use exogenous information. We can use extra variables. And we saw on day one, when we looked at the Victorian electricity data and we visualized the patterns that existed in that data set, we saw that it had a very strong relationship between temperature and electricity demand. But so far, we haven't been able to use that extra information of electricity demand in our forecasts. So here we'll be able to use regression with extra information, but there are some problems with extra information and forecasting as well that we'll see. So we'll start with the basics again. What is a linear model? And we'll catch up on some time here because I understand that you're all somewhat familiar with the regression model already. A regression model has two main values for the analyst. Unlike most benchmark methods that we've seen so far, and a lot of forecasting methods that we'll see in the future, regression models are really good at explaining the patterns that exist in the data. They're interpretable models, which means you can look at the coefficients and see how that relates to the historical data and the exact patterns that you'll produce in the forecasts. Compare that to perhaps the naive model, and when Bahman looked at some coefficients from that model, there wasn't really anything interesting to understand what's happening in the data. And that's because the model was so simple that it was just copying yesterday's price or the last observation. A regression model, however, when you include a trend in the model, the coefficient for that trend will tell you the slope, how much increase or decrease there is for every observation in frequency. So if you've got monthly data, it'll tell you every month the sales increase by $10, for example. Now, the other purpose, of course, is to forecast from a regression model. And in fact, for all of the models that we'll see for the rest of the week, they're all usually used for forecasting in the time series domain. The only exception was the model that we saw yesterday, which was the STL model. And we usually use the STL model to decompose the data, and it's not used very often for forecasting. However, there are some ways in which you can use decompositions to help your forecasts by simplifying the patterns, looking at perhaps forecasting seasonally adjusted data instead of the entire data set with seasonality. Now, there's two main types of regression models. Usually we'll be looking at multiple linear regression models because we usually want to have multiple patterns of the data set captured by this model. But first we'll start with simple linear regression model where there is only one coefficient to look at. So I previewed this yesterday when we looked at the STL decomposition model. But if I have on the y-axis our data set and time on the y-axis, and I just drew this with a bunch of scattered points. If I treat xt, my predictor, if I just simply treat this as time, you may have seen this before, then I will get a good fit through the center of the data. It's a linear regression, simple meaning one coefficient, L meaning linear, or one regressor I should say, there's two coefficients including the intercept. And then lastly, regression. So this linear regression will give you a straight line. And we talked about yesterday how sometimes the trend isn't always straight. Perhaps you had a trend that went up like this. Population often looks like this. GDP anything with inflation or growth tends to have this exponential curve. A simple linear regression model won't fit this data very well. It's just going to draw a straight line through this, and you can imagine if I was to produce some forecasts from this model, it will be well under what we expect the true value to be, because it's not able to capture that exponential curve. However, we had the solution that we talked about yesterday for localized regression models, STL. We can, of course, log the data or use a Box-Cox transformation, and then the log of y will convert this curved line into a straight one. Now, of course, it's not always log. It might be a square root. It could be Box-Cox with lambda equals 0.2. We learned yesterday how to find the best possible transformation in order to simplify the patterns in our model. So even though the simple linear regression model and the multiple linear regression model can't handle exponential shapes very well, we have a trick. We can transform the data, simplify the patterns, and therefore we can produce more reasonable forecasts, which when we undo the transformation will give us a nice exponential forecast. Okay, so the basics, we have our left-hand side of the model, which is y. Yt is what we're trying to forecast. And then we have an intercept, exactly the same as the LM function in R. We have a 1 to represent my intercept, and then I'm going to add on the regressor x. And then that will estimate a coefficient, a linear relationship between y and x, and it will estimate this regression model. What this model doesn't capture will be left in the epsilon t. This is my residuals. Everything that wasn't captured by the model ends up in the error term. And we'll have a close look at the error term today in order to understand what is a good model and what isn't a good model, because we want to make sure that this regression model is better than the benchmarks. Okay, so of course, when we estimate a model, we put the hats on these coefficients because they're now estimated values. And because we're making a prediction, there should be a hat on Yt here as well. We don't know what the actual value is. And so we no longer have the epsilon t because we don't know how wrong our prediction was. But these coefficients, especially this one here, is very interpretable. You can say for a 1 unit increase in x, we have a beta 1 hat unit increase in y, on average holding all else constant. You may have heard that phrase before in regression models. It's exactly the same when we apply this to a time series. The only difference here is instead of an I subscript for an index, we have a T subscript for time. And you'll see for all of our regression models, all of our time series models, we have time subscripts in our models. Okay, this is a generic slide relating to how we estimate those coefficients, beta hat. And essentially, we have all these observations. In our case, these will just be a time series. And then we find the line that minimizes the least squares. So we square the error, epsilon t. We add them all up to get the sum of squared errors, and we want to minimize that. And there's a few mathematical tricks. It's a closed form problem, and this can be done very quickly. So we can let R calculate the optimal values for us. Here is the optimization function. Here's the sum of the squared errors that I was talking about before. But if my model was Yt equals beta naught plus beta 1 xt plus epsilon t, in order to figure out what this EI is, or epsilon t in our case for time series, all we need to do is move all of these terms over to the left. So that will give us epsilon t is equal to yt minus beta naught minus beta 1 xt, which is exactly what I have here. So I just square that, add up all the values, and that is my sum of squared errors. Of course, we don't want very large errors, so we want to make this number as small as possible. We want the sum of squared errors, the SSE, or often called the SSR, the sum of squared residuals, to be as small as possible so that our model is as most accurate as it can be. Okay, here's some data that we'll be looking at. This is United States consumption, and we're relating this with income. So there's two different time series in this data set. In fact, there's a few more. Let's have a look at this in R. So as before, I will load in the FP3 package. And then having a look at the US change data set, we can see this is some economic indicators from the USA. And of our interest today is consumption and income. So I can plot consumption like we did in day one. There is that data there. I can also plot income. And these two time series have some similarity. And we're going to use this similarity to predict consumption. Now I can look at both of these variables at the same time using vars, consumption, income. That will show me them side by side, which is useful for multivariate plotting. Or I could do auto layer. Auto layer will take a data set, in this case US change, and add a variable to the plot. So there's consumption. I might set the color here to be red. And then in blue, I'm going to add income. So that's one way you could produce that plot quite simply. And you can see these two follow a very similar pattern. When the consumption reduced, the income reduced as well. When income recovered, consumption went up again. So you can see these two lines follow fairly closely. And we can use this in a regression model to produce a good estimate of the data. A better way to do this is to use the tidyr package and use the gather function in order to convert it to a long form, or you could use pivot longer if you've used that before as well. There's lots of options to produce this plot. Now, the other way in which we could visualize this is by not plotting it over time. Often what we'd like to do when we're relating a two time series is to just plot the data against itself without looking at time at all. So for this, I'm going to use ggplot directly. On the x-axis, I'll put income. That's my x variable. My response variable, y, is consumption. And then I'll just use a scatter plot using g on point. And of course, I need to add the data in as well. So US change is piped into ggplot. And here is the relationship in a scatter plot. And we talked about correlations in day one. This one has a slight positive correlation. You can see there's a big cloud of values in the middle, but generally these values are increasing. So as income increases, consumption increases as well. Now, if you've used ggplot, you might have seen geom smooth before. This fits a regression model. And if you look at the method here, LOS, that should sound familiar from what we saw yesterday. This is a localized regression model being used on this data set. So we estimated a model here between these two observations, and we got a negative slope. We estimated between these observations, positive slope, positive slope. Generally, you can see that the data is increasing where we have data to support that. But we're not going to use localized regression today. We're going to use linear regression. So we can set method equals LM. And this is fit the model y on x using a simple linear regression. And we can see the straight line relationship. The intervals from this fit are very narrow, suggesting that it's a fairly strong relationship. Despite the large cloud of points, it's definitely an increasing relationship between income and consumption. So how do I model this relationship? Well, just like we did in the previous session for the benchmark models, we're going to take our data set, US change, and pass it into the model function where we will specify our model. And remember, the models are all in capital letters. So this time we're going to use a time series linear model. Let's try that out. I will put some of this code in the chat as well. There you go. Oh, I just realized I haven't sent the day 3 code to everybody. The Bahman's code I've just put in the chat as well. Okay, so having a look at US change, I've got lots of variables to consider. I'm going to pipe this into the model function to estimate a model on the data. And then I'm going to use a name for this model to make it easier to use later. So I'm going to call this LM, my linear model. TSLM for time series linear model. Predicting consumption, we're putting consumption on the left side of the tilde, the formula, because that's what we want to predict. And we're going to predict consumption using income. Now, I could put an intercept in here, just like the LM function in R, which you've probably used before. The intercept is default included in the model. So including it explicitly is good, but it's not necessary. And when I run this code, you'll find that I get a Mabel, a model table, with a single TSLM model inside. So I'm just going to save that model as fit because we'll have a look at it closer. One way that we could look at it is to use the report function. The report function is a great way to visually see all of the important information about the model. It's not so useful for looking at a large collection of models. This only works when you've got a single model that has been estimated, but it's a very nice, clear way of reading the coefficients. So if I use report on fit, you'll see what I get is the summary statistics of the residuals. We have the coefficients that were estimated. That's my beta hats from the equations before. So we can see the beta hat for the intercept was 0.5. But perhaps more interesting is the intercept, is the coefficient for income. What this says is for a 1%, because these are in percentages, a 1% increase in income leads to a 0.27% increase in consumption, on average, holding all else constant. So these models are very interpretable. Another way that you can get these coefficients, which is possible for when you're working with large models and many models all at the same time, is to use the tidy function. The tidy function will give you, instead of a report giving you written out responses, it will prepare it in a data set. So if you've got multiple models, this will give you all of the coefficients from all of the models in the same place. This is a great way to compare different models together. So that's simple linear regression. Multiple linear regression simply is the same thing, but we now have several or multiple predictor variables. The idea here is that when we're forecasting our response variable, in our case consumption, we expect it to have a linear relationship with not just one different time series, but multiple time series. And you can see in this data set, US change, that we didn't just have income in this data set. We might also want to use consumption, predict consumption using unemployment figures. So there's lots of options that you can consider when you're using a multiple linear regression model. Now, this might be tempting to add a lot of different regressors. You can add as many as you like, and your residuals, if you do this, will be 0. But that's not necessarily a good model because you have the problem of overfitting. Overfitting is when you estimate the model using too many parameters, and what the coefficients are for will just essentially replicate the data. And when you overfit, the model isn't going to be good at forecasting. And it's also not going to be very interpretable as well. Multicollinearity is also a problem that you might have heard of before. We've got some more time to look at this a bit later. But if you're adding lots of variables, those extra variables that you're using to predict the response, the y variable, might be related to each other. So if there's a correlation between your x variables, then you could have modeling problems as well. And that's known as multicollinearity. For the simple linear regression model, all we had was yt equals an intercept and a regressor. But for a multiple linear regression model, we now have all of these extra x variables. And this is almost always what we use when we consider regression for time series forecasting. So once again, yt is what we're predicting. That's the response variable on the left side of the formula. The xt's here are my predictors. And I need to know the values of these in the past to estimate the model. But if I'm forecasting with this model, I'll need to know their value in the future as well. And this is a big problem with using regressors in time series forecasting. Sometimes these predictors are just as difficult to forecast as y itself. So you need to choose predictors carefully such that they're well known and easy to forecast or obtain in the future, and informative for how y might behave in the future as well. That's a tricky thing. But just like before, we use x1 plus x2, all of your regressors on the right-hand side of the formula to specify this model. And just like before, this epsilon t is whatever's left over, what the model wasn't able to capture. It's known as our residuals or our errors, and we assume that epsilon t is white noise error term. We assume that it's IID normal with a mean 0 and a variance sigma squared, a constant mean of 0 and a constant variance. Now that's not guaranteed, and we'll need to look at some tests to see if epsilon t is white noise and see if we are working with a good model that has captured all of the information available. So once again, we'll be looking at the ACF plot to evaluate if our model is doing well. Just like before, to estimate these models, we want to find the predicted values for each of these coefficients. We use the sum of squared errors. So SSE, or the sum of squared residuals, is another word for this. And just like before, when we moved the predictors over to the left-hand side, now we're going to move all of the predictors in order to square them and calculate the sum. Trying to reduce the errors, make them as small as possible, will give us the best model, minimizing the squared errors, also known as least squares, in order to estimate the coefficients. And this is really quick. Again, there's a closed form solution, so this happens almost instantly. It's just a matrix inversion problem. So you've probably seen almost all of that before without time series involved. But when we're using time series to make a forecast, we have one extra dimension that we normally don't have in ordinary regression. And that is, of course, time. So at the start, for the simple linear regression, I talked about this idea of having xt simply equal to time itself. And this is a really powerful way to introduce a trend term in my model. If my data was looking like this, this is yt, and this is t, it's a natural thing to use a trend term to estimate this relationship. And to do this, my predictor variable can simply be t. That's a number that will start at 1, and for every observation, it will increase by 1. And so this will give us the marginal change, or the slope, for every new observation in time. Now, because this is a linear regression model, we end up having a linear trend. And trend isn't always linear. You can see that this trend that I've drawn is changing a little bit. The slope is getting steeper and flatter throughout different points in time. So a localized regression like we saw yesterday is a bit better for capturing these changing trends. But in next week, tomorrow I should say, when Bahman talks about exponential smoothing and ARIMA, you'll see even better methods for capturing the trend, which are useful for forecasting, especially when that trend is changing over time. Now, in order to add t to the model, we have y tilde x plus t. You can't just do plus t. R doesn't know what t is. Instead, we have a special function to help create this time trend for you, and that is trend. So you can do plus trend with the brackets because it's a function, and that will automatically calculate and insert the trend term in your regression model. Now, I promised before that this model would be able to do both trend and seasonality. So to add seasonality to the model, we use the season special. So you can plus season as well. So that's predicting Y using some regressor, maybe income, plus trend, plus seasonality. And suddenly we have several terms in my regression model. That's why we need to use a multiple linear regression term. Now, if you're familiar with regression models, the season function uses dummy variables, and we'll learn more about dummy variables later. So let's have a look at US consumption again. This was the one we were looking at before in R. Previously, we were using just consumption and income, but we also saw that there were some other variables that could be used. Here's a GG pairs scatterplot matrix, and you can see that a lot of these variables have significant correlation. When we're trying to predict consumption, you can see it has a fairly strong correlation with income, but an even stronger correlation with production and an inverse relationship with unemployment. So by using more than just income, by using the other variables in my model, I will hopefully get a better prediction and a better understanding of US consumption. So here's how I would do this. I'm not using any time series patterns yet. I'm not using trend or seasonality. I'm just using additional information, my predictor variables. So let's go back to R. Here was the code that I used to do the regression model before, and I want you to try and change this model and add on the extra regressors in order to produce a multiple linear regression. And then I want you to have a look at the coefficients of the two models. So use the tidy function with your new model. I'll give you some code to get started. Fill in those question marks and see if there's a difference between the coefficients that you get for income between these two models. And this is a good time for any questions if you have any. Okay, hopefully that wasn't too difficult. One of the variables that I'd like to add is production. So simply I write production on the right-hand side of this formula, of this tilde. And I also want to add savings and unemployment. So then I run this code. Again, from day one, you can use Control Enter, or you can highlight this code and click Run. And then I can look at the report of this model as well. Or I can look at the tidy to get the coefficients directly. Now, usually when I'm comparing models, I like to do both models in the same function, the same model function. And Bahman showed you how to do this to compare the benchmark models in the previous session. So I will take the model code, but this time I'm going to create two models. One is going to be multiple linear regression, and the other is going to be simple linear regression. Don't forget this comma to separate the two models. The simple linear regression is just going to have income like we saw before, but the multiple linear regression will have the other predictors too. So when I call this estimate these models, I'll give it a name, and then I can use the tidy function. And you can see I now get both models in this same table. You can see that the report function doesn't work. Instead, it gives me the goodness of fit measures, the glance output. Doesn't work, and it doesn't work because we have greater than one model. We have multiple models for this Mabel. But the tidy function is a great way to compare the coefficients of multiple models. In this case, we can see for simple linear regression, the intercept coefficient, the income coefficient was 0.27. And we made an interpretation on that before. However, that interpretation was wrong because we had omitted variable bias. We didn't include enough extra information that was also related to consumption. And so this effect was reduced because it was capturing some of the effect of unemployment, for example. People don't have as much income when they're unemployed. And so this bias was introduced to our model. Incorporating all of the extra information we have, you can see the income coefficient has gone up from 0.27 to 0.74. That's a much larger coefficient now. And you can see a 1% increase in income actually leads to a 0.74% increase in consumption, holding all else constant, holding production and savings and unemployment unchanged. Whereas before, we didn't have that in our model, and so we weren't able to hold them constant. And that accounts for the difference that we had in the coefficients. So it's important to be careful when choosing the models and the terms in your regression, because it can make a substantial impact on not just your interpretation, but also the quality of your forecasts as well. Another useful plot that you might do is to look at the fitted values compared to the data. This is our first look at the accuracy of a model. How closely was our model able to predict the actual data of consumption? And the fitted values are forecast just one step ahead. In this case, for quarterly data, it's forecasting just the next quarter ahead, and it's seeing how accurate it was in this plot. Now, to make this plot, we can plot the underlying data, which was autoplot consumption. And I'm going to give this a nice orange color. I guess just orange. I need to set the color equals to orange. Okay. And then a useful function, in addition to tidy, is augment. We'll use this function quite a lot. Augment will, just like we did augment for principal components, add some information to the original data set. Here's consumption and time. That's what we're predicting. It's added on information from the model. In this case, the predicted values, one step ahead fits, the residuals, and the innovations. So let's plot the fitted values and see how closely the predicted values, y hat, is to consumption, the actual data. So I can do auto layer, like we did before, with the augmented data, and I'm going to plot the fitted values. I'll put this code in the chat as well. Sorry if you're having trouble copying this code. Unfortunately, there's no way for us to add these to the Q&A ourselves. I see a few questions did come in. One question, can I clarify again, are we holding predictor constant in a regression model? That's right. So when we're interpreting a coefficient, this coefficient for income, 0.74, is when we say it is increasing consumption by 0.74%, that is holding constant production, savings, and unemployment. This is saying if income was to go up by 1 and production, savings, and unemployment weren't to change at all, that's what we mean by holding it constant, then we'd have an increase in consumption by 0.74. The exact same interpretation that we have from non-time series or cross-sectional regression models. Another question here is, if there is not a significant relationship between the response and predictor, can we still use it? You can still use it, but it's not going to add anything useful to your model or your forecasts. So a good idea is to look at the p-values here. Now there's a fair few assumptions underlying these p-values and see if they're less than 0.05. So in this case, income was significant for simple linear regression, and income and savings are really significant. Production is significant. Unemployment is also fairly significant. Just above 0.05 in this case. So most of these terms are significant at a 5% level. All of them are significant at a 10% level. Okay, I think that was all the questions for now. Thank you again for everyone copying the code into the questions and answers, for everyone to copy. So what I've done with this code that I've just put in the chat for you all is to plot consumption, our underlying data, and then I've added on top of it the fitted values from both of my models. And the simple linear regression is in blue, and the multiple linear regression is in red. And which one of these two models follows the orange line closest? Which of these two models is most accurately describing the data? That's exactly right. You can see the multiple linear regression model in the red is following the orange line when it drops down, whereas the blue model, the simple linear regression, wasn't able to react to those changes. It didn't have enough information to match the data quite closely. Now, you could be concerned that this might be overfitting, but with 4 predictive variables and the significance that we saw of them, it's not overfitting. There's not enough regressors in this model to overfit this many observations. We still have a lot of degrees of freedom available. So the other useful plot of this is to plot the data along with the fitted values. This is ignoring time entirely, and you can see the data and the fitted values match each other quite closely. This is where you can get the correlation, which is similar to the R-squared of the model that you might have seen before. In fact, if we use the glance function, this is the last of the 3 different functions we use, tidy, augment, and glance. You can see you get the R-squared values where the simple linear regression model only explained 15% of the variance, whereas the multiple linear regression model explained 77% of the variance. And when we use the adjusted R-squared, so that we avoid overfitting, you can see the multiple linear regression model is still substantially better. Another approach to see which model is better, which Bahman will introduce more in the future sessions with ETS and ARIMA, is information criterions, AIC, AICC, and BIC. And for these, we want it to be as small as possible. And you can see that the multiple linear regression model, -457, is much smaller than -205. So the multiple linear regression model is better in every way that we can see. Now here I've just compared two regression models, a simple and a multiple regression model. But you could also do the same thing with a benchmark model. You can add in the naive model and see which one is performing better. We'll see that in a later day. Now, I promised you on day one that we'll be using the ACF plot again. You'll see it come back several times, and that is because it's a useful indication of if there's any information left in the data. So now, instead of plotting the fitted values, we're plotting the residuals. That's the epsilon t. It's whatever's left over. Or for precision, it's actually ET, where ET is equal to YT minus Y hat T. In most cases, there's no difference between ET and epsilon T. It's only subtle differences if you've got a transformation, for example. Epsilon T is on the transform data. ET is what you usually think of when you have an error, the actual minus the predicted value. So here I'm plotting the residuals, and I get, with a TS display, this is a new type of plot, but it's all plots that you've seen before. We have a time plot at the top, with the y-axis is now the residuals, and on the x-axis we have time. And in this first plot, we're really looking for no pattern at all. So in this first plot, can you see a trend? Can you see seasonality? What patterns can you see? So in this case, I don't see anything. It looks like it's centered around 0, which is excellent, because remember the assumption is that we have a normal distribution. We'll look at the normal later. But the mean is 0. That's one of the assumptions that we made. So IID, normal 0, sigma squared. And you can see from this first plot of the residuals, everything is centered around 0. So this assumption is correct. We have a 0 mean based on this time plot. What about the variance? Is the variance constant? No, exactly right. So we have some periods with a large variance and other time periods with a small variance. So what we have in this case is subscript t. The variance is changing over time. And this is bad. This says that our model could be improved and the coefficients that we've interpreted before aren't the most reliable. In most cases, when it comes to forecasting, this isn't a problem. What this means is that our intervals might be slightly wrong. So while our point forecasts are probably okay, because our mean is 0, that one there, our intervals, our uncertainty, is probably not ideal, because the variance is not in line with the assumptions. It doesn't follow the assumptions. How can we tell the variation in this diagram? You can see in this area of the residuals, they're spread out, whereas in this area, they're not very spread out. So the variance here is larger than the variance here. So because they're not equal to, this variance is not constant. It's changing over time. And that poses a problem for our model because we're assuming constant variance. And in fact, the coefficients that we get require and assume that to be the case. How do we check for normality? So I've got this normal assumption here. Which plot do you think would be a good one to use to check if the residuals are normal? Here we want to check all of the assumptions in the data. Exactly, you can look at the histogram. Does this histogram look normal or not? Excellent. So yes, this histogram looks fairly normal. It's got a single mode. There's maybe a little bit of stuff missing here, but it is fairly normal, exactly right. So this is close enough for our purposes. If it didn't look normal, Bahman was talking about using bootstrap forecasting. We'll try to see that later in the week, but that's a solution that you can use to make your forecasts, especially the distribution of your forecasts, more accurate. So I'm going to give this normal a tick of approval. What's the last assumption that we need to check? We've checked the normality, we've checked the mean, the variance, but we haven't used this plot yet. What could we use this plot for? Okay, so one person suggested correlation, that's right. So the ACF is the autocorrelation function. It's not skewness. You could look at for skewness in the histogram, and if it's skewed, then it wouldn't be a normal distribution. You could see if there was a trend in the ACF. That would definitely be a problem with one of the assumptions of the model. You could also see a trend in the residuals here, but we're really looking for subtle details here in the ACF. So we probably won't see any trend or seasonality unless our model missed something really big. So which of these assumptions here, I've written out all of the assumptions on the errors, but I haven't ticked one of them off yet. Which of these needs to be ticked? What's an assumption about our errors that we haven't tested yet? This is a tricky question. It's something to do with the IID step. What does IID stand for? That's right. So it's IID stands for independent and identically distributed. So we've already actually checked the identical. We've checked the identical by seeing if the mean is 0 and the variance is sigma squared all the time. So this kind of got a tick for the mean and a cross for the variance. I'll give it a tick cross. We've also checked the distribution. That was normal, so we get a tick of approval for that one. But what we haven't yet checked is if it's independent. And it's independent if there's no autocorrelation. So we want to make sure that the residuals are not related to any other residuals. They need to be independent. And how would we check that using the ACF? So we want to ask if this is independent. So each of these are a correlation that we have in our time series. These blue dashed lines represent a 95% test. And yes, that's exactly right. So if we have all of our ACFs within the blue dashed lines, that says that there is no significant autocorrelations remaining in my residuals. And so therefore, all of the autocorrelations aren't related to each other and are therefore independent. So in this case, we get a tick of approval. The ACF is independent, or ACF shows that the residuals are independent. So putting all of these combined, we get a pretty good result for our model. It's normally distributed, mean zero, it's independent. The only problem here is that the variance is changing a little bit over time. And what this means is that our forecasts, especially the variance of those forecasts, might be a little problematic. Our interpretations are also problematic when we interpreted those coefficients because it violates the assumption of a regression model. This is a great point. One of the spikes is outside the boundaries, so this one failed the test. But you can see this is a 95% test. So we expect 5% of the observations to be outside the line just by chance. And because we've got 22 lags shown here, we expect 1 or 2 to be outside the blue dash lines, and that's okay. We can ignore that one. What you would be concerned with is if you had one of these lags, like lag 1, being incredibly strong. Even though it's just 1, it's so far away from the blue dash line that you can't ignore it. Usually the ones further back in the past, the higher order lags, we don't worry about as much. But we do pay particular attention to the seasonal lags. In this case, it's obvious we don't have any seasonality. Lag 4 for quarterly data is almost 0. But if we had lag 4 being significant, then this would suggest we might have some seasonality left over. So there's a few lags that we pay more attention to, but in this case, this lag 7 being slightly significant, we don't care. It's not a problem. We still give this the tick of approval. Okay, so I hope that helped answer a couple of these questions. How do we know if the ACF is independent? You're hoping that the blue dash, the lines, the vertical lines in the ACF are within the blue dashed boundaries. At what number should we be worried? When do we know the seasonality? So with the ACF plot, we saw in the previous day, day 1, if we had lag 4, lag 8, lag 12, all of these being positive and significant, that says that we have seasonality. We also saw if we had all of the values being slowly decaying. This is a trend. In this ACF, we don't have either of those patterns, which says that we don't have trend or seasonality, but we still might have some very subtle patterns that aren't trend or seasonality. They're autocorrelations. And we'll see the ARIMA model, which works really well to capture all of these little subtle details of autocorrelation. But what we're looking for here to see if it's significant or not is if enough of these are outside the boundaries. And there's a formal statistical test that we can use for that as well. Do we have that slide somewhere? I'll just see if we've got a slide for that. I don't think we do. Okay, so I won't spend much time on the formal test. There's a lot of assumptions for this test as well, so it doesn't always work very well. And we've just done all of this with checking assumptions. But the formal test that you can use is a Lung box test. A Lung box test allows you to check if the autocorrelations of the residuals are significant or not. So we can use the augment, fit both, and then features on your innovations, Lung box, and then we say how many lags we want to check. So let's check 4 years of data, 16 lags. And this will do it for both models. So here's the code for that one. And here you can see that the simple linear regression model had a p-value less than 0.05. So this fails the test for the simple linear regression model. But the multiple linear regression model had a p-value of 10%, which is greater than 5%. So we fail to reject, meaning that this one's okay. If it's less than 0.05, we have a problem. Let's have a look at the GGTS residuals of the simple linear regression. Fit, select, SLR, GGTS residuals is another way you could do this. Plot, fit both. Just a moment, Bahman. So here's the simple linear regression model, and you can see in the ACF we have two significant lags, and they're pretty far away from the blue dashed line. So this is significant, and you can see that is why it fails the test when we consider Lungbox. So this allows you to formally test if we should be worried about the autocorrelations of the residuals. Bahman, did you want to add anything?
Sorry, Mitch. No, I just wanted to ask if you could just explain what was the difference between that inov and that resid in the augment.
Yeah, I was sort of avoiding this one, but maybe you could talk about it more when you do multiplicative exponential smoothing models.
Sure, yeah.
The main difference is when you do a regression model, yt equals beta naught plus beta 1 t plus epsilon t. Epsilon t here is your innovations. So this is dot inov. Your residuals, et, is equal to yt, your actual data, minus y hat t. And y hat t is equal to, so I'd put the yt minus there as well, yt minus y hat is equal to beta naught hat plus beta 1 hat t. So in this case, the innovation residuals and the residuals, response residuals we call them, are identical. And you can see that in the augment results. So if I do augment fit both, you can see that these two columns, resid and inov, are identical. All the values are the same. But what if I did a log transformation? So in my model, if I do the log of yt, it'll be equal to a linear beta naught plus beta 1 t plus the innovations, epsilon t. But when I do the response residuals, that's this one here. This is response dot resid. Oops. Dot resid is the response residuals. Epsilon t is the innovation residuals. In this case, the et, response dot resid, doesn't change. It's still yt minus y hat t. And that will be very different from log of yt and epsilon t, the innovation residuals. So when we're checking the assumptions of our models, we're always looking at epsilon t. Epsilon t is the assumption IID normal 0 sigma squared. Epsilon t, et, response residuals, is just useful for saying how accurate the model is, which we'll see later. This also shows up when you look at exponential smoothing models, ETS, which Bahman will remind you of tomorrow, I think it is. Okay, for my case, I'm using weather parameters to explain plant disease after to forecast the future decades based on future predicted weather. Cool, that's a nice application. I'm not sure if there was a question in there, but if there was, maybe you can clarify it. Okay, I don't think there's any more questions, unless you had anything to add, Bahman.
No, I think just that question about the predicted weather. Yeah, just you need to be careful how far actually you forecast it, because the weather forecast, as you know, from let's say 2 to 3 days after would be quite challenging to forecast, and that will affect a lot your forecast as well.
That's right. So to summarize the assumptions that we've checked, we've got var epsilon here. Epsilon t has this normal 0 sigma squared assumption, and we can check that using the TS display function. We check the time plot, the ACF, and the histogram for each of the aspects of this assumption. And this is the steps written out. So we check the residuals are uncorrelated using the ACF. We check the histogram to see that they're normally distributed. And we check the time plot to see the mean and variance is constant. You can also do residual scatter plots between residuals and your predictor variables. And this is a good way to check for endogenous variables that might exist in the data, which can also cause problems for your regression model. Okay, it's also possible, this is to reduce overfitting, it's also possible to select the predictors. Maybe you've got hundreds of different predictors that you might use in your forecast for a regression model, and it's nice to have a way to select which predictors are most valuable. Now, you've probably heard of the R squared before, the coefficient of determination, and this variable is useful to explain how much of the variance is explained by the variance in the predictors. Now, if you add a new variable to the model, the R squared value will always increase. So it's not a very good way to prevent the model from overfitting. If you just maximize R squared, you would put all of the variables into your model. That's because the R squared doesn't consider degrees of freedom. So the best R squared would have as many parameters, as many regressors as you have data points. For this, we use the adjusted R squared, which incorporates K. Now, K is the number of predictors. So as we increase the complexity of the model, as we add more variables, then this R squared will get smaller. So this controls the effect of adding too many predictors, and we can find the best model and the best set of predictors without overfitting using adjusted R squared instead of R squared. And there's some nice statistical properties for that. An even better approach that you might have heard before is cross-validation. And for time series and regression models specifically for time series, there's a really nice way, a shortcut of doing cross-validation that makes it really quick. And that can be found in the CV statistic of the glance output. So if I look at glance of these models, CV from glance, you can see that the cross-validation statistic of the multiple linear regression, the smaller the better, 0.1 compared to 0.35, the multiple linear regression model is much better. Now we'll see information criterion more later, but you can also use an AIC, Akaiki's information criterion, and this also includes K. This time, if you have K, it's going to increase the AIC, which is also bad. We want the AIC to be as small as possible. Usually we'll use the Akaiki's information criterion, a corrected version of it, which adds a slightly stronger penalty for the number of predictors, which is better for small sample sizes. So it's a slightly improved version of AIC, and I almost always use AICC to choose my models. And you can see that in the glance output for the models as well. So you can see the multiple linear regression model had the smallest AICC. So here's the code for how you would calculate that. I will put it in the chat as well. And based on this, we can try to find the best model by adjusting the parameters in the model. So we can start with a model using all of the variables. That's what we have here. and then we can remove some of the models. So MLR1, I'll just give it another name. Maybe I try removing savings. Maybe I don't think savings is important. Now if I glance the model, you can see that MLR1 has much higher AICC, and therefore savings was actually important, and I should have kept it in the model. So maybe I try removing a different variable instead. Maybe I keep savings, but remove unemployment. I'll give this another name, MLR2. And you can see the AICC for this model, -455, is so close to MLR1. MLR, the model with all of the coefficients. Now, according to AICC, it's still better to include all of the predictors in the model, but unemployment really isn't doing much. It only dropped it by 1 AICC. So if you really wanted a simple model, you could consider removing unemployment because it doesn't change the accuracy of the model very much. So you can use AICC in order to identify the best possible model without having the problem of overfitting. Okay, a couple of questions. Can I explain epsilon and ET? Unfortunately, we don't have time for this one, but the recording will be made available. So I recommend that you look for the recording and go back and review it at your own pace. But this relevant question about the AIC, is it dedicated to comparisons of many models, or can it be used to interpret the quality of a single model? Usually we use it for comparing models. It's not very interpretable on its own because it's based on the log likelihood and a transformation of the log likelihood based on the number of parameters in the model. So usually just for comparison.
Just maybe it's worth noting that it is for comparison between models across the same family. Let's say, if you have ETS, you can have, and we will see tomorrow, you can have about 30 different models, and it could be used for that, but then you cannot actually use it to compare, let's say, ETS with ARIMA families. But again, with an ARIMA family, we can have 1,000 different ARIMA models, and AIC could be super helpful there. So we will discuss a little bit more about AIC tomorrow as well.
I guess I don't have the AIC statistics for a naive model, but that's exactly right. You do have to be careful when comparing AIC across different models, and you also can't compare it when you have different transformations. So if I have a log transformation here, my innovation is completely different now, and you can see that the AIC has changed completely. And this might look similar to MLR1, but really it's just a completely different number. It's not comparable at all now. The CV is equal to the cross-validation statistic. This is leave one out cross-validation. You fit the model without one observation, and then you predict that one observation and see how accurately you did, and then you add it all up, combine it, and you want the smallest possible value. Deviance, I'm forgetting. Bahman, do you know what the deviance was? For regression, it's usually in cross-sectional.
Oh, yeah. To be honest, I haven't seen this in the output. Is it?
It's a summary statistic that people use quite often. You can find information about this online. It's not specific to time series, but the deviance is commonly used in cross-sectional modeling to see how accurate the model has fit the data. It's not something I use very often.
Yeah, I've never used it before.
Okay, we're running out of time, so I'm going to speed through. We want to look at some forecasts, of course. So let's forecast with regression. Now, there's a bit of a caveat, a bit of a problem when we forecast with regression. And that's because when we're doing an ex-ante forecast, when we're predicting the future genuinely, we also need to know the future of the predictors as well. And this isn't easy. What is the future value of income. Well, that's just as difficult to predict as the future values of consumption. So making a forecast from this model, we might have found that the best model was MLR1. So let's select MLR. Sorry, the first one, not MLR1. It should have different names. MLR0, let's call it. So this was my best model based on the AIC that we're looking at before. Let's make a forecast. Maybe I forecast 5 years ahead, and it doesn't work. And this is because it couldn't find income. We need to know the future values of income, production, savings, and unemployment just to make a forecast of consumption. So that's a lot of work in order to get a forecast here. Now, some of these variables like weather, you might be able to tell in advance a little bit, like maybe a week ahead, you can get a reasonable prediction of what that might be. Other variables like sunrise, it's really easy. But most of the time, regression models are difficult to forecast with if you're using extra information. If you're doing retrospective forecasting or ex post forecasting, you have what happened next. You know the future. And this is useful for studying what happens in the model for forecasting. So this is where forecasting becomes a bit easier for regression, but usually you want to predict stuff that you haven't seen before. But what is nice is if you're using the trend function or the season function and any other calendar effects, you know what the future values of trend and seasons will be. You know that next month will be October, and then November, and then December. So these you can forecast very accurately. In fact, you don't need to forecast them. We just know what month will be March, for example. So usually we use regression with these deterministic regressors. If you don't know what happens next, yeah, Bahman?
Sorry, Mitch, I just wanted to say, if you want really to practice this, so you have to look at the apply exercise, because there are variables there that you need to basically produce the forecast for them, because we use them as a predictor in the model. So please look at the apply exercise later to practice this a little bit more when it comes to the using predictors in regression model.
Yeah, that's great. We've got a lot of good exercises for this one. So if you don't know what the future value might be for one of your predictors, you don't know what the future income in the United States will be, you could do scenario-based forecasting. And remember from day one when we talked about time series data and the whole purpose of forecasting, it's to help make decisions. So scenario-based forecasting can be really important to make decisions based on time series modeling. This is, for example, used for when I did COVID forecasting to save lives in Australia. The government really wanted to know how many people would get sick if they were allowed to travel freely. So we put this in the model. What would happen if people weren't restricted at all? They could go see their friends, they could go to the shops whenever they want, and suddenly everyone gets infected. So that scenario allows them to understand the dangers of a certain decision. Then they might consider the possibility, the scenario of only allowing people to travel once a week, or perhaps within a 10-kilometer radius or a 5-kilometer radius. We can set up all these scenarios and make predictions for how many cases there will be, how many deaths there will be, how busy the hospitals will be. And that is really critical for making decisions at a government level. So you can imagine how, even though it's hard to know the exact value of what these future things for income or the spread of COVID-19 might be, you can impose some scenarios and use that as a decision-making tool, which is arguably better than just making a forecast without the predictors. Now, another way is to use a predictive regression model, and this uses lagged predictors, so what happened yesterday, in order to predict the future. So rather than using the contemporaneous effect, meaning the exact same time consumption and income, we might predict consumption using income from last quarter. And that will allow us to predict income 1 quarter ahead, because we know what the 1 step ahead value for the last quarter would be. Now we can do that in R. I don't have a slide for it, But to do that in R, it's very simple. We can, instead of using income, we can use lag of income. So let me write a new model. We will go a little bit over time, so I understand if you do have to leave. So MLR lag. Instead of using income contemporaneously at the same time as consumption, we can use lag. And this will use one-step lags. You can change this to two-step if you like, with a comma. And then lag unemployment, like so. Now, I hope this works. If I forecast just one step ahead, it doesn't work. I need to improve my code just a little bit, but what we could do is set up the new data for US change and just add in dummy values for the step afterwards. Income equals NA, production equals NA, savings equals NA. I just need to say that I really don't know what's happening next, so don't try to forecast more than one step. Have I made a mistake? That looks okay. Maybe I have a contemporaneous effect or something's not quite working there, but that's the strategy at least. I will look into this more throughout the week. But if you use lagged predictors, you'll be able to use the most recent observation to make your forecast because it hasn't yet been used for your model. And then you should be able to forecast it very simply, just forecasting one step ahead. That might not work for a while, but this one I've shown above, I'll make sure it works shortly. That's what happens when you do live demos. Sometimes it doesn't work. But the other option here, very similar to what I just showed with new data, is that you can set up scenarios. So I'm going to forecast the next 4 steps ahead, but because I'm using extra data, I can't just say H equals 4. I can't say go 4 steps ahead. I need to say what the future values of income, savings, and unemployment are for the next 4 steps. So in this possibility, this scenario, things are going down. The income goes down by 1, savings by 1/2, and unemployment doesn't change in either scenario. Whereas the other scenario where things go up, instead we have an income increasing by 1 and savings increasing by 1/2. And then we can forecast with both of these scenarios, if it goes down or up. So forecasting these using auto layer for the up scenario and the down scenario, you can see if things go up, the consumption stays about the same. But if things go down so quickly, the model will react very quickly and consumption will drop suddenly. And this happens in the past as well. So it's reasonable to expect this to happen again. We have sharp drops in the past when the other inputs like income were dropping as well. So that can help drive decision making as well by playing around with the possible scenarios. Correlation, causation, and forecasting. You have to be very careful when you build these models not to include anything that doesn't make sense. So there's an excellent website here for spurious correlations. These are things that look very similar. You can see there's a time when in 2007, both of these two variables increased. They're pretty similar here, dropping in 2003, and most recently they're increasing a lot. But these two variables have nothing to do with each other. This is the number of Nicolas Cage films, an actor, and this is the number of people drowning in swimming pools. They're completely unrelated, but if you included one of these variables and tried to predict the other in a regression model, you would get a fairly accurate model. It just wouldn't continue into the future. You have no reason to believe that the swimming pool drownings are being caused by Nicolas Cage's film appearances. So this model is completely unreasonable for forecasting, even though it might look good in the fitted values. Another thing to be careful with is correlation is not causation. So you have to be very careful when you say that Nicolas Cage has caused swimming pool drownings. That's not the case. They just happen to be correlated, and that's a spurious correlation. Causality is a much more difficult thing to prove, which often requires some scientific testing. Very controlled scenarios to understand what one thing affects another and exactly how that does. So I also mentioned multicollinearity. This is a regression cross-sectional kind of term. So you might have come across this again without time series already. But this happens when two of the predictors in your model, two of the things on the right-hand side, are very similar. So they're similar with each other. And this makes it hard for the model to piece apart exactly which variable, which predictor affects the response variable. So this makes your coefficients a little bit less interpretable and less reliable. So here we have, if you have multicollinearity, the coefficients might be wrong. They probably are wrong. You can't rely on any of the significance tests like the p-values. You can't. There won't be a problem with predictions. You're just going to have to provide more predictors than you probably need to. And removing some of these multicollinearity variables can help, or combining them together into a single variable can also help solve this problem. Okay, you've also got outliers. You can use the weights argument to downweight them, very similar to how we used robust equals true, but we won't pay much attention here. Often I wouldn't remove outliers just because they're outliers. I see people automatically removing outliers and fitting models, making forecasts. That's not good, because if I were to go back here and see this outlier and this outlier and this outlier, and remove them entirely. So now my data looks like this. I make a forecast and I'm suddenly really confident in my predictions. That's because I've removed all the outliers, and suddenly the model thinks there's no possibility that something like that could happen again. So you're kind of misleading the model about what possibly could happen in the future. And this could cause things like global financial crises. If you're not considering the GFC in your historical data of the model and you make a forecast, then that forecast is assuming that a GFC won't happen again in the future. Same for COVID. If you ignore the effect of COVID causing everything going to zero, you're ignoring the possibility of a possible pandemic in the future, which might not be completely accurate. Okay, this slide's about what if you have 44 regressors. Often I work with hundreds of regressors. This causes a lot of difficulties for model selection because there's trillions or uncountably many combinations of models that could be selected. So in this case, we might use lasso or ridge regression in order to simplify the models and not overfit the data. Okay, lastly, I want to talk about some useful predictors. We talked about the time trend and seasonality using dummy variables. Here is dummy variables in more detail. It doesn't have to just be dummy variables for seasonality. You can also use dummy variables like you normally would in a regression model. I've used it for forecasting the number of fancy hat sales in a tourist town of Australia. There was a festival happening in March every year, but sometimes they were thinking maybe we should cancel the festival, and they wanted to see how their tourism sales would change if the festival wasn't running. In this case, you would have a dummy variable for if the festival was running in that month or not. Here's how we use it for day of week or seasonality. If it's a Monday, it's a 1, otherwise it's a 0. If it's a Tuesday, it's a 1, otherwise it's 0. So this helps identify what day of the week it is for the model. But you also have to be careful of the dummy variable trap, which you've probably heard of before. The season function and all of the dummy variable functions for categorical variables automatically handles this. You just won't see one of the values in the regression coefficients. So you can see for quarterly data, there's 4 quarters, but we'll end up with 3 coefficients in our model because of the dummy variable trap. Monthly, 12 months, 11 dummies. Daily, 7 days of the week, 6 dummies. You can also remove outliers using dummy variables. So you can say, if COVID, then dummy variable. So that will help control the effect of COVID in your model. It also is useful for public holidays. If it's a public holiday, set the dummy variable to be 1. So you can also use spikes and step changes. So a spike is similar to that outlier dummy variable. It's just immediately a 1 in the regression, in the predictor. Whereas a step change is an intervention. So maybe we have a control measure. We for COVID, prevent people from, require people to wear masks. So it's not just a single outlier, we have to wear masks. It's now a continuous period of time. You have to wear masks. And then maybe later they remove that requirement. So this is a step change. Sometimes the step changes go back, for example, when the mask mandate was removed. Other times it might just be a forever change, like you've built a new infrastructure, you've built a new train. That train's not going away. You might also have a change of slope. So we've seen this a few times where you might have an increasing trend, a flat trend, and a downwards trend. You can handle this with trend using the knots argument, but we'll see better ways to do this with better models tomorrow. So I'm not going to get into the details of that. Here's some more dummy variables, different holidays that you might consider. Again, if it's Christmas Eve, set the dummy variable to be 1. Every other day of the year, it'll be 0. Just like regression models, you can use interaction effects between 2 variables. That works for anything. And we've talked about lag predictors and how useful they can be already. And this is just an example of lagged predictors that we might use. Make a scenario forecast, 3 different scenarios, and that'll do for today. So if you had any final questions, I'll stay on for like 5 minutes or so. There's a question here. Is there any other way to access the materials without going to the website? There's problems in Cameroon. Send us an email and we'll find a way to get you these materials.
Yeah, could you please try if you can access the GitHub link? Because that's another way to get all the materials. I just shared the link there. So if you get the link, you can also download all material as a zip file.
Yeah, I wonder if it's a problem with not being able to access GitHub. So you might not be able to access GitHub pages, but hopefully you're able to access github.com. But if you're not, you can reach out to us via email. We had our emails in the first slides. Maybe Bahman, you can reach out by email as well.
Yeah, absolutely. Yeah, just if you could.
The GitHub link is working. Problem solved.
Okay, great. Yeah.
Okay, a couple more questions. Does that mean seasonal dummies have n-1 coefficients? That's right. Usually we use the letter m to describe the number of seasonal periods. So m equals 12 for monthly data with an annual seasonality. But we'll always have 1 less variable than the number of seasons because of the dummy variable trap. Is the current section on dummy variables related to feature engineering? Somewhat. You can create some features like a holiday feature that uses dummy variables, but feature engineering isn't limited to dummy variables. You can engineer a continuous feature as well. The advantage of regression models compared to a lot of other models that we'll see this week is that it can handle extra information like regresses. Any other questions for today?
Right.
Okay, we'll end it here. Thank you, everyone. This is my last seminar that I'll be giving. The remaining 4, the last 2 days, will be delivered by Bahman, so you can look forward to that. He'll be going through some different time series specific models that you probably haven't seen before, which can handle all of the changing trends and seasonalities and even the subtle autocorrelations that we've been talking about so far. So thank you, everyone. I'm going to end the recording here. If you had any last questions, I'll still stick around and answer them.